In this video, we will discuss about the approximation order of elements and specifically higher order elements. Now, let's start with a very simple example of a cantilever beam. Now, let's say we have a certain cantilever beam which looks like this, and you have an end load P acting on the beam. Now, from our experience, we know that the beam is going to deflect in a certain way which looks like this. There are different ways of representing this beam by using a certain approximation order for a finite element analysis. If I consider one element, then I know that if the element is a linear element in one dimension, then I will be able to form the solution which sort of looks like this. It will just be a linear solution and will not match the final solution or the exact solution that I'm looking for. Now, in the same way, if I want to get to a better solution, then I can use the same linear element, but I can put two elements instead of using a single element. So what will happen is that I will be able to form, let me do this with a different color. I will be able to form a single element which goes like this and another single element which goes like this. So I will get two elements which are getting me closer to the exact result. However, it's not really exact. Now, if I want to get even closer to the final result, then I can look at another combination of three elements where I would see that three linear elements would be used in this way to form a solution which is coming even closer. So in the first case, I had one element which basically made my solution look like this, just straight. In the second case, I had two elements which gave a little tin here, a kink over here, and then the third one I had three elements which made it slightly better but still not good enough. So if I keep increasing the number of elements so that I can get closer and closer to the solution, is called refinement of the mesh. That means I am increasing the number of elements so that I can get closer to the exact solution by reducing the error to a minimum. And this is one of the ways of getting convergence. That means we want to get to the exact solution in a certain way. So this is one of the ways of getting a better solution. However, you can also get a solution faster and a better solution by just changing the approximation order of the assumed function. And those elements that have a higher order of approximation behavior to match the exact solution are called higher order elements. So basically, as I've told you as a recap, there are two ways of getting to your exact solution faster or in an improved way. One is by increasing the number of elements, and the other method is by increasing order of approximation function. And of course, when I say order, it will be an polynomial function. So these are two ways by which you can improve your results and get closer to convergence. Let's look at one of the examples. We have already looked at a linear function. So of course, linear function is the first order. So that means it's not a higher order, it's just a baseline equation or a function that we looked at for approximation order. So I'm going to use the same element, which is basically one dimensional. That is a truss element, but I will now start imposing a higher order of behavior on this element. So for example, we take this truss element being an axial element. That means we are still considering only 1 degree of freedom at each node for the entire element, leading to a linear interpolation function of order 1. So we just look at here as a basic axial truss element. So the characteristics that we know of are that they have 1 degree of freedom at each node. This is one of the simple explanation for an axial element, and the other one is that it can be described by a linear interpolation function or a linear shape function. Of course, interpolation function is just another name used for a shape function. In the same way, if I just consider, I'm just going to use another example here. If I say I have a beam element, this is a beam now, and I have 2 degrees of freedom at every node as we have seen before. That means the beam has 2 degrees of freedom per node, so a total of 4 degrees of freedom for the entire element. So in this case, I can say I have 4 degrees of freedom. So to get to 4 degrees of freedom for the shape functions, I need to use a cubic interpolation function. So basically, these are the order of the approximation function that I am talking about. Similarly, if we want to use higher order elements for any of these elements directly, we have to make a small change, or we have to make a small assumption. And that is the assumption that we are going to talk about when we discuss higher order elements. Let's just go ahead and say that we are going to put our focus only on the one-dimensional axial element, because as I've shown you before, it's much easier to work out on paper. So let's say we want to take this truss element. Very simple. I have 2 nodes I and j, and if I want to use a higher order interpolation function on this truss element, in order to be able to do that, I have to introduce an extra degree of freedom. If I want to introduce an extra degree of freedom in an axial element, then I have to introduce an extra node somewhere along the length of the element. So let's take for example an element which looks like this. We have 2 vertices at the ends, and we take one central node extra, which we call k, because I would like to find out what is the unknown degree, the displacement u at k as a result. Okay, so there are different ways of doing it. Either I could have just taken the length of this element and I could have said I want to divide this into 2 different elements. One would be element A ij, and the other one would, or ik, and the other one would be element B kj. This was one way of doing it that we have already dealt with before, and that is to do with mesh refinement by increasing the number of elements. And the other way of doing it is by introducing a degree of freedom by introducing a node k, but instead of saying that they are 2 different elements, we will say that they are the same element. It's exactly the same element now. The element hasn't changed, but there are 3 nodes in the same element. So in order to describe this one element, I will have to change the approximate behavior of the function. Now when I described a single element that was ij, yeah, I'm going to write it with one color so it's easy. Previously, for one element with 2 nodes, therefore 2 degrees of freedom total, I could write the approximation behavior for the element to be equal to C1 plus C2x. And this was a linear interpolation. Okay. Now, in the second case, I have introduced 1 degree of freedom and 1 node in the same element. I haven't changed the element. Now, I still have 1 element, but instead of 2 nodes, I have 3 nodes, and therefore 3 degrees of freedom in the entire system. So my new approximation function will have 1 extra term. So I have C1 plus C2x plus C3x square. And this therefore becomes a quadratic interpolation function. So this is another way of adding a degree of freedom without actually refining the element or the structure. So now the rest of the process still remains the same. Let's start with the approximation function. So we have C1 plus C2x plus C3x square. We know that at x is equal to xi, because this is in the direction of x. So you have ui, uk, uj. So at x is equal to xi, u is equal to ui. At x is equal to xj, u is equal to uj. And at x is equal to xk, u is equal to uk. We know this already. So by substituting these three conditions 1, 2 and 3, into equation A, which is here, we will get 3 equations solved simultaneously to give us u of element is equal to shape function ni times ui plus shape function nj times uj plus shape function nk times uk. Of course, once you substitute equation 1, 2, 3 back into A, you will get 3 different equations. You will solve them simultaneously, and then you would have to rearrange them in such a way that you get your shape functions ni, nj, and nk for the corresponding degrees of freedom in the system. So this is basically a very important result that you were looking for. Now we can also write this in a matrix notation, ue to be equal to n u, but actually you can also write it in full just for one time, ni, nj, nk, or in easier way you can write ni, nk, nj, because that's a easy order in terms of how it's also distributed in the figure. So this is how you would write it, and then you can also check the values of the shape function yourself. You put it in, you check if it is correct, etc. And I will just write them down here on this page just to finish off how you find out the shape function and what do the shape functions look like, because it would bring us in directly to the next part or the next little section that we are going to discuss on Lagrange interpolation functions. So the shape function si ni, or the first shape function, is going to be 2 by L square x minus xj times x minus xk. Nj, which is the second shape function, is equal to 2 by L square times x minus xi times x minus xj. Xk. Well, since I have nk as a middle node, it will be different. Then I have to write here nk is equal to 2 by L square x minus xi and x minus xj. And finally nj, which is the last node, will be given as minus 4 by L square times x minus xi, x minus xk. So in this way, you can easily derive the shape function for a higher order element. The only thing you need to always remember is that you have made a change in the way your element is behaving right here. What you're doing is you are introducing this extra node over here, which is changing the interpolation function that you used for approximating the element behavior. So this is a very simple example for a higher order element. You can also use higher order elements for other complicated elements, higher order approximation order for higher order elements. And the change that you're going to make, of course, is by adding extra degrees of freedom. And if you attach extra degrees of freedom to an element, you also have to add nodes to the element. And these nodes are internal nodes in the element. So it's very easy to start with a higher order interpolation function to get the same results as you do with multiple number of elements in a mesh refinement. Now, don't be of the idea that there is one method that is better than the other. So I can always ask you a question of whether higher order approximation is better than a mesh refinement using more elements. So as you can imagine, if I have the cantilever beam problem, yeah, if I have this cantilever beam problem and I am loading it at its end, and I do get this nice behavior with a delta, which is the deflection at the end, I can get this either by using a higher order approximation of a single element. So I say this is a single element, but I introduce certain number of degrees of freedom. So I basically go from UE from being quadratic to a much higher order. It could be a 6th order or a 8th order, depending on how many degrees of freedom I'm going to add. But at the same time, I could just use mesh refinement from 1 element to 20 elements, and all these elements would still be linear, or in this case, in the case of beam elements, quadratic elements, and I would still get the correct answer. I could still get to that point. So this makes a very big difference in in how you compare the two different methods. In some cases, it may be faster to achieve some kind of convergence, if you're looking for convergence of a certain result by means of higher order elements. That means you could get to the converged result here by using certain number of elements, and you could also get this same result much faster sometimes or most of the times by using a higher approximation order. So it completely depends upon the type of function or the type of problem that you are dealing with, which has a more influence of a higher order approximation or by using maximum number of elements. So it could be one or the other. You can always try different methods to check which one suits you better, which one is much faster for you. But of course, there should be a certain highest order approximation that you want to use so that it doesn't become computationally too expensive in any case. So of course, you choose judiciously of what you want to do, but again, there is no direct answer of which method is better than the other.